Hello, everyone. So the first speaker today is Riccardo Pellarin. So Riccardo is a CNRS researcher since 2015 at the Structural Informatics Unit at Institut Pasteur. Before that, he spent many years at UCSF in the lab of Andrzej Sali, when he contributed to the development of the IMP, Integrative Modeling Platform, and particularly for the development of the Python modeling interface, which is a very convenient library to prepare simulations with different type of experimental restraints. And today he will talk about Bayesian modeling in integrative structural biology. And so you can ask your question in the chat Q&A, and then we'll answer them at the end of the talk. So Riccardo, please.
Hello. Hello, everybody. Thanks for inviting me. Thanks for organizing this with symposium, and thanks also Juliette for inviting. So I have to share my okay. So you see that, right?
Yes.
Perfect. Sorry, I have to put that first slide first. Okay, so so I show a little bit of my what I do as a researcher, which is mainly I'm interested in integrative modeling of macromolecular complexes. So let's start to see what is a macromolecular complex. So here, I don't know if you see the mouse pointer.
Yeah.
Okay, good. So this is like the architecture of an entire cell, which has been determined by focused ion beam scanning electron microscope. Nowadays, we can actually get the intricate architecture and organelles within a eukaryotic cell and depict it in this beautiful way. Imagining that you can zoom in, actually, you can zoom in, if you have a higher resolution in situ microscope, ideally you can start to see like these machineries which are working by cooperatively associated proteins and other macromolecules. Now, for instance, this is a depiction by good cell of the what is going on and the interplay between different components of a cell. It has been determined recently, for instance, in this case is nuclear pore complex, which is a kind of donut shape or pore, which is sitting on a nuclear envelope, and it's like mediating the transport of material between the inside of the nucleus to outside and vice versa. So now this system has been resolved by integrative modeling, and I will show you later what it is about. And it shows like the intricate substructures that are making up this system. It's made of more than 400 proteins, about 60 megadalton, and it's made of several hierarchically organized subcomplexes here. So it's very fascinating domain of research, as you can see, and but the problem is that, well, normally, what you normally do is like getting information about a macromolecular complex and their structure using elite techniques such as X-ray crystallography. And you saw before in the introduction by Juliette, high resolution electron microscopy, as well as always solid state NMR. But in many cases, a single technique is not possible. And the measure of that, you see that constantly every year, about 30% of entries which are deposited in EMDB are low resolution map, higher than 5 angstrom. And of these low resolution map, practically very few are associated with a deposited PDB structure. That means that in many cases, due to, I don't know, many reasons, for instance, the lack of a good sample or any other reason, is not possible to resolve the architecture of the complex or interpret the density. So what if we cannot determine the structure of a single technique? So you apply a method which is called integrative structure biology, which can be organized into four stages. The first stage is the gathering of all information about your system. Either it can be low resolution or high resolution, whatever you can get about your system. It can be interpreted into a structural restraint, like low resolution electron microscopy or localization of protein by immunoelectron microscopy or affinity purification pull down of protein-protein interactions. Anything, it's useful. Then in a computer, you start representing your system by domains, which maybe you have information on high resolution information. You might want to also constrain them into rigid bodies or leave some parts which are flexible into flexible beads, strings. And this will set up your degrees of freedom for a system. And all the information you gathered at the first stage will be encoded into a scoring function, which is the function which ranks practically the input information. It ranks the model according to how well they fit the input information. After you have the degrees of freedom and the scoring function, what you do is normally sampling these models. So you let them simulate, kind of simulated according to this scoring function, and assemble in the computer. And you will get like some high scoring models, which you will afterwards in the fourth stage analyze by clustering, by looking at where proteins are localized in the space, more probably, by validating the models using cross-validation or external validation, and create testable hypotheses. And these testable hypotheses are, with this testable hypothesis, you can create, you can design a new experiment that will be helping to increase the information at the first stage and therefore refine the structure following. Now, as you can understand, you can use different data sources from theoretical data sources, like as you see before, structures from homology modeling or AlphaFold or Rosetta, as well as also evolutionary direct coupling from evolutionary covariance, but also low resolution SACS, FRET spectroscopy, and other. All these methods bring different spatial and temporal resolutions. And then, of course, the problem is that since you have this heterogeneity of data and data with high uncertainty, also the final model will be affected by a degree of uncertainty, which is something you don't normally see in, let's say, high resolution structural determination, which normally ends up with a single conformation, as it is in the case of cryo-EM or X-ray diffraction. The uncertainty is sometimes negligible or less important. But in this case, the uncertainty is very important because the data, first of all, is by definition sparse because it's incomplete. We cannot have enough data to determine the position of all atoms and everything because of the lack of high resolution information. They are noisy, normally noisier than it happens in cryo-EM or high resolution cryo-EM and X-ray crystallography due to imperfection, due to the false positives and so on. They are ambiguous due to the fact you have multiple copies, for instance, of proteins, or the fact you might have uncertainty in assignment of restraints to parts of the protein or the complex. And they are the fact that you have heterogeneous samples. It makes the fact that you have multiple states, multiple subpopulations, it will give you incoherence in the data. So how do we produce these models with this uncertainty? So as we said, the uncertainty is important. So the model of the uncertainty of the model must reflect the uncertainty and the sparseness of the input data. So we won't have a best structure given the data, but we will get a distribution of structures given the data. In other words, what you are interested in is determining not a single structure, but let's say conditional probability of having M, where M is the model. It's a set of all 3D coordinates of atoms or other model parameters which are defined for your system, given the input data. Your input data can be anything at this point. So the best way to use with best framework to represent a conditional probability and treat it mathematically is the Bayesian framework, where if you treat your conditional probability of M given D and other information as a as a posterior probability, you can use it. You can practically express it as a product of two terms, as you know, the likelihood and the prior. A model here comprises a structure of the coordinate, but also other additional parameters which are necessarily included when you define Bayesian likelihood, for instance. And the likelihood is a function that encodes the agreement of the model with the data, with the input data, through another function which has to be determined and has to be built up, which is the forward model. So this forward model is practically the way we back calculate the data from the input model. So if we have the coordinate model and want to get, for instance, the actual cryo-EM that this model would have been generated, this will back generate this kind of, let's say, model data, which you compare directly within the likelihood to the real data to create a kind of probability distance, probability of producing this data using the model. The prior defines the probability of a model given any other knowledge, which is not the data. And the scoring function finally is the negative logarithm of the posterior, and therefore, sorry, is the negative logarithm of the likelihood plus the negative logarithm of the prior. So, so now the problem is to sample this complex multidimensional function. And since you are not interested in a maximum posterior model here, you will be interested instead in the region where models are relevantly statistically probable. So the peak, around the peak of this multidimensional probability. So to do so, we practically evolve the system using a Markov chain Monte Carlo to generate samples from this distribution, simply using that. So now let's go to the integrative modeling. So a typical example, I would say, the most compact way you can get information to and have information from a system is to combine, let's say, high resolution information about the subunits through X-ray or, I don't know, other structure prediction, such as AlphaFold if you want, and the homology modeling, and cross-linking mass spectrometry, which you will see later, probes the proximity of residues belonging to the proteins, and electron microscopy data. So the crosslink will provide you distance restraints between the subunits, and the electron microscopy will provide you kind of an envelope where you can assemble your subunits. So as you can see, this will be kind of puzzle that we have to resolve in 3D. And you will end up having a structure like that for the RNA polymerase II, which is not high resolution, but it's still a bit blobby, but still informative. You know, everybody knows what is the electron microscopy. So it's you have a sample which is deposited on a grid in cryogenic conditions. And after you pick up images of your, and collect images about your protein, you cluster them into D-class averaging and use them as tentative projection of a 3D density. And this is the way you build a 3D single particle reconstruction from the individual images. So in the past, we've been working on the framework for a Bayesian electron microscopy restraint, which uses the data, the target electron microscopy map, and individual structure of subunits are represented by rigid body or flexible, with some flexible parts. So the input electron microscopy density map has been translated into a Gaussian mixture model. And the individual subunits also, they have two layers of representation. One layer where they represent the individual residues at the coarse-grained level, and another layer where each, let's say, protein is represented by a Gaussian mixture model. So we developed the mathematics for a Bayesian scoring function, which evaluates in the likelihood the overlap between the model GMM and the data GMM, and quantify it. And the desirable attribute of this scoring function is that it will be depending on the resolution of the input data. So the strength of this scoring function will depending on the resolution, which is something we didn't have before. So therefore, if you integrate this with other sorts of information, including crosslink, it will give a strength which is proportional to the information content of the cryo-IM data. For the crosslink data, you have a chemical crosslinking coupled with a mass spectrometry. And the experiment is simply that you get your in solution, your complex of, you let it react with a linear linker with bifunctional endpoints. This will react with moieties of the protein, bridging them, covalently bridging. Then after digestion, you will use practically standard proteomics to detect which peptides were linked. And every peptide that was linked were peptides that were, let's say, proximal in the input structure. And of course, this kind of information suffers from many issues. The sparseness, because it's just provide a list of few proximal residue pairs. It's not very dense. The noise, because it provides some let's say identification will suffer from false positiveness. The ambiguity, because the spectra can be identified and interpreted in multiple ways. And of course, the incoherence, because you might have multiple structural subpopulations in the sample. So one problem we have to deal while we were building the Bayesian scoring function for this kind of data is the fact that you have conformational flexibility and you have what we call cross-linked states. So you don't directly observe the native conformation of the system, but you observe something which has been chemically modified, particularly, let's say, a plethora of microconformations of little variants of the native states, where presumably some conformation has been, let's say, stabilized in some unknown, let's say, non-physical or unbiological conformation. So this brings to a kind of level of complexity where sometimes you see crosslink which don't make sense, but it could be that because it has been, the crosslink is sticking somehow on the surface of your complex. So we had to define a kind of order parameter, a Bayesian order parameter in each, on each residue or on each domain, that tell us a little bit what could be the kind of structural variability at each point of your native state of your protein or your complex. And this brings us to the idea of the forward model for the crosslinks. So here you have two, let's say, two residues. And what it takes into account this forward model is like the fact that you might have also coarse-grained beads and not individual residue defined by atoms, and the fact that you have this continuous heterogeneity problem. And we solve this problem by practically using 3D Gaussians that are with an unknown variance, which has to be determined during the Bayesian process, optimized together with the modeling. And therefore, the forward model is a kind of probability of forming, let's say, a crosslink between two, these two coarse-grained residues. So the probability that distance between any point between these two coarse-grained spheres is less than a certain length, which is the length of the crosslinker, given the distance between the two residues, given the variance of the two uncertainty 3D Gaussians, and other parameters. So the benefits of a Bayesian framework to data modeling is manifold. In particular, working with that, I realized the Bayesian framework is able to gain a robustness, even introducing noise and signal at the same time. So by doing this experiment, it was clear that if you use clean data without noise, such as like a high confident crosslink but sparse, with less data, you will end up with some very unlocalized positioning of your proteins. But if you include noisy data and good data, so it's difficult to really tell whether when you decrease the confidence of crosslinks, you are picking up good crosslinks or bad crosslinks. You increase the denseness of the data, you end up having the right solution. Because the Bayesian framework, what it does is practically infers the level of consistency of any data within the prior knowledge and within the bulk of the data. So if there are outliers, normally they are cleaned out, they are removed from the modeling itself. So you end up having the right solution. So everything has been developed on an integrative modeling platform with Benjamin has been mentioned, which is an open source platform and initiative, which includes several features such as the fully documented backtracking, unit testing, as well as also tutorials. And what it provides is a low-level language for developing modeling software. So practically provides objects which can be assembled together like a Lego construction set to build your protocol for modeling. On top of this integrative modeling, we build this Python modeling interface, which practically includes protocols and standards, which has been already, let's say, published for building these macromolecular complexes from the data. That includes Bayesian scoring functions, multi-scale representation, Markov chain Monte Carlo sampling, and a list of different validation and analysis of these models. So this has been used in several examples, which has been published. And in particular, I wanted to mention the architecture of the ribosome with the EF3 complex, which has been practically determined only using a few crystallographic structures of domains, homology modeling of other domains, cross-linking mass spectrometry, electron microscopy, a low-resolution electron microscopy map. We ended up having this very low-resolution positioning of different domains of the EF3 around the ribosome, which has been confirmed later by cryo-EM, initially by a low-resolution cryo-EM of 6 angstrom in 2016, and more recently in this year on a 2021 work on yeast pre-initiation complex. And another example is the structure of yeast mediator complex, which has been determined using the crystallographic structure of domains, homology modeling, cross-linking mass spectrometry, electron microscopy maps, and using electron microscopy labeling, yeast-2 hybrid and immunoprecipitation for validation of the model. And again, we add like a low-resolution architecture of the whole complex, which was perfectly then in the following found in a high resolution level. So this is to show that this integrative methodology works and has also very good predictions. And also another story is that we could use practically the mediator model to build a higher order model. In this case, the mediator with the RNA polymerase II pre-initiation complex. So practically we merge the structures, the bundle of structures of the mediator complex together with other subunits to build a larger component. So now, last slide, what is the missing level? I think we have a lot of information, a lot of tools to build macromolecular complexes out of ideal conditions. And I think what would be desirable in the future is to work more at the cellular in situ structures and at the mesoscopic level, what is really missing, and it can only be depicted using artworks, like in this case. But we have a lot of information coming and emerging, like proximity labeling, in vivo cross-linking mass spectrometry, in situ cryo-electron tomography, fluorescence microscopy. And I hope that all this information together will be helpful to build a kind of model, or let's say posterior model of the organization of the organelles in the cell. With that, I want to thank you all and thank a lot of people I've been collaborating with in the past years. Thanks so much.
Thank you, Riccardo, for this nice presentation. We have time for questions. I don't see. Do not hesitate to ask your question in the chat for Riccardo.
Benjamin, I cannot use the chat.
Okay.
I would like to ask a question if possible.
Okay, go ahead.
Riccardo, I wanted to know, when you integrate several types of experimental data, some of them have a lot of false positive. Do you specify it from the beginning? Do you put a special penalty on this type of data?
No. The idea is, like, first of all, every single piece of data is its own, like, Bayesian treatment. It has to be investigated beforehand. So, for instance, cross-linking mass spectrometry is like a piece of information that can contain false positives. The presence of false positives is reflected in the likelihood function directly, but without giving exactly what could be what entity, what quantity of false positives. So you have normally mathematically a free parameter, which has to be fit together with all the other parameters, including the coordinates and everything else. And this parameter tells what is the quantity of false positives, or it's proportional to the quantity of false positive into the data that you have. And you do it practically by practically quantifying the synergy of your cross-linking mass spectrometry experiment or is2 hybrid or whatever with the rest of the data. If there is synergy, if there is a consensus, practically, most likely there are not false positive. And this parameter will go to 0, practically. And if instead they are like inconsistencies, they will be removed practically automatically during the sampling, and will be down-weighted practically. I don't know if I answer your question, Juliette.
Yeah, thank you.
And François Coste is asking complementary question, is asking if you are setting or choosing the priors.
Yes, the priors are very simply, in my case, priors are, for instance, the structure of subunits for which we know with good confidence the conformation. They are assembled into rigid bodies, and this is a prior information. And also, and it is not really, we don't doubt that. We don't give a high confidence to that. So the difference between prior and likelihood is that any piece of data that we may give some level of confidence is into a likelihood, and everything which we give for granted is into a prior. Another piece of information which is in the prior is like excluded volume, like the fact that proteins cannot compenetrate each other is a form of prior information, and we give it for granted. It's a piece of information we cannot put into question.
Okay. I think we have Sergey who also wants to ask a question. So maybe I will ask the producer.
There is another question from Fabrice Leclerc. You see?
Yeah.
Yes.
In case of
You go ahead.
Yeah. In case of conflicts between the data, how does the protocol deal with that? Do you have some detailed feedback and information on the resolution? What kind of data was prioritized? Yeah, this is an important point. It's the balance between the different pieces of information is really important. So when you have conflicts, if the likelihoods are, let's say, well organized, well developed in a sense, they are the way they do, they operate a kind of repression of the information. So, for instance, if you have one likelihood per crosslink and one likelihood per, for instance, for the cryo-EM data, and you have some conflicting crosslink, so what happens is that the parameter that's practically measuring the noise of individual data points will tell you that a certain point, in order to let's say, in order to satisfy the most of the data, he has to sacrifice something. And this is a mathematical, it's just due to the the form of the likelihood, the way you form the likelihood. It's true that in some cases you might prioritize some information and not other. This is something we try to avoid, and that's why we develop, for instance, cryo-EM likelihood, which is kind of trying to be kind of trust, whose weight is proportional to the number of, to the resolution practically. So the more resolved is the cryo-EM, and the higher is the weight. But it's possible that you're prioritizing something automatically. Normally, you don't prioritize anything. In principle, everything has the same information and dignity, if you want. This is because you don't know a priori what is better, what is worse in a certain condition. But afterwards, inevitably, technically, what happens is that some data will be a little bit more promoted than others.
Okay, Sergey, you can enable your mic if you want to ask a question.
Yes, thank you, Riccardo. Unfortunately, I couldn't ask the question in the chat. I have a question. If you do not know the distribution of the probability of the original data, for example, you generated a structural ensemble by some perturbation techniques, which doesn't have, the probability wouldn't have any meaning. Can you still apply the Bayesian technique?
But normally, so if you don't know what the likelihood, or if you don't know the posterior, normally the posterior you never know. It's like
you don't know the posterior.
You never know the posterior. It's something you never know. It's if I know the posterior, the problem is to know the posterior, to sample the posterior, so that you explore it by sampling. Because if you know the posterior, of course, that you solve the problem. So let me see if I can get back. So it's the same problem that you have when you do molecular dynamics simulations, right? Where you have a force field, but you don't know what will be the final most populated state, right? You have to do molecular dynamics simulation to know that. Same happens here. So you have the restraints, which are like information, which are information.
In the molecular dynamics simulations, in Monte Carlo simulations, you do sample a certain ensemble with you know that it's a Boltzmann distribution.
Yeah, exactly. And you do the same here. Imagine that this likelihood function
in other cases,
so the posterior will be like so the likelihood function will be a sort of like the force field term, right? If you want. In your case, it could be springs. In a molecular dynamics simulation, would be springs or anything. But here it's more like a spring based on the data, and also prior are like another kind of force field term. So coupling everything together, all these terms, you end up having a kind of free energy, if you want, or you will get a Boltzmann distribution, but you don't know it beforehand. And what you do normally in molecular dynamics simulation is to sample, right? Sample the distribution to have an idea of what are the populated states in a system. And you do the same here. To get the posterior, you have to kind of sample you have to sample the coordinates of the system.
Okay, if we want to keep
Okay.
the time, maybe you could continue the discussion during the coffee break.
Sure,
Yeah.
sir.
Thank you again, Riccardo.
Welcome.